A long-standing quest for science and technology has been to develop electronics and information processing that operate near the fastest timescales allowed by the laws of nature. A promising way to achieve this goal involves using laser light to guide the motion of electrons in matter and then using this control to develop electronic circuit elements, a concept known as light wave electronics. Remarkably, lasers currently allow us to generate bursts of electricity on femtosecond timescales, that is, in a millionth of a billionth of a second. Yet, our ability to process information in these ultra-fast timescales has remained elusive. Now, researchers at the University of Rochester and FAU have made a decisive step in this direction by demonstrating a logic gate, the building block of computation and information processing that operates at femtosecond timescales. The feat reported in the journal Nature was accomplished by harnessing and independently controlling for the first time the real and virtual charge carriers that compose these ultra-fast bursts of electricity. The researchers' advances have opened the door to information processing at the petahertz limit, where 1 quadrillion computational operations can be processed per second. That is almost a million times faster than today's computers operating with gigahertz clock rates, where 1 petahertz is 1 million gigahertz. In recent years, scientists have learned how to exploit laser pulses that last a few femtoseconds to generate ultra-fast bursts of electrical currents. This is done by illuminating tiny graphene-based wires connecting two gold metals. The ultra-short laser pulse sets in motion or excites the electrons in graphene and importantly sends them in a particular direction, thus generating a net electrical current. Laser pulses can produce electricity far faster than any traditional method and do so in the absence of applied voltage. Further, the direction and the magnitude of the current can be controlled simply by varying the shape of the laser pulse, that is, by changing its pace. The research groups have been working for several years to turn light waves into ultra-fast current pulses. In trying to reconcile the experimental measurements with the computational simulations, the team had a realization. In graphene-gold junctions, it is possible to generate two flavors, real and virtual, of the particles carrying the charges that compose these bursts of electricity. Real charge carriers are electrons excited by light that remain in directional motion even after the laser pulse is turned off. Virtual charge carriers are electrons that are only set in net directional motion while the laser pulse is on. As such, they are elusive species that only live transiently during illumination. Because the graphene is connected to gold, both real and virtual charge carriers are absorbed by the metal to produce a net current. Strikingly, the team discovered that by changing the shape of the laser pulse, they could generate currents where only the real or the virtual charge carriers play a role. In other words, they not only generated two flavors of currents, but they also learned how to control them independently, a finding that drastically augments the elements of design in light wave electronics. Using this augmented control landscape, the team was able to experimentally demonstrate for the first time logic gates that operate on a femtosecond time scale. Logic gates are the basic building blocks needed for computations. They control how incoming information, which takes the form of 0 or 1, known as bits, is processed. Logic gates require two input signals and yield a logic output. In the researchers' experiment, the input signals are the shape or phase of two synchronized laser pulses, each one chosen to only generate a burst of real or virtual charge carriers. Depending on the laser phases used, these two contributions to the currents can either add up or cancel out. The net electrical signal can be assigned logical information 0 or 1, yielding an ultra-fast logic gate. The researcher says that it will probably be a very long time before this technique can be used in a computer chip. But at least we now know that light wave electronics is practically possible. This new, potentially transformative technology arose from fundamental studies of how charge can be driven in nanoscale systems with lasers.